Yes, please interact with me. Yes, I will be really happy to, to answer your questions. Okay, so today I want to start this course. I don't know if I think I would give a hopefully very little short introduction of the formalism that I'm going to use, okay? So let me start with how, so we introduce, let's say, vectors as linear operators on functions, right, of H. So a vector in general relativity is a linear operator, and it's a differential operator in the sense that if I apply on two functions, this is UF times H plus FU of H. So we recognize this one as a differential operator, and then we write the U as in this form here, and this has to be considered as a basis for the vector space, actually. Now you say, why am I doing this one why am I doing this kind of introduction for linear perturbation theory? Because we have to, in doing perturbation theory, we have to describe two objects. One is the gravity point, and the other one is matter fields. And both must be treated in terms of linear perturbation theory. So when we study a theory, we had to know how to deal with the matter fields. And when I say matter fields, in cosmology, we usually mean perfect fluids, mostly, okay? And perfect fluid itself is not a fundamental kind of matter Lagrangian, right? That in the standard model, there is no perfect fluid action. But in cosmology, we do have it because it's a very convenient way to describe a matter. When I say matter, radiation and dark matter, baryonic matter in a three-dimensional Benson-Walker background, actually. Right. So we know this construction here. So we will call this EA to be the basis for the vectors, and so forth and so on. Now it's there is also another point here. So these are vectors, and then there are one forms. And one forms are defined as an application, linear application from vectors to real numbers. So I will call by Greek letters mostly with the tilde one form which applied on U will be given by this object here, and this is a real number. And zeta works linearly. This will be zeta A U1A plus zeta A U2A. So it's a linear application from the vectors to the real numbers. Okay, so we know that we can introduce the gradient, and the gradient is one form whose components are just the partial derivative with respect to the variables, the coordinates xa, times omega A. Omega A is the one form such that applied on the basis gives the identity, actually. Okay, having said this, actually, when we apply the one form on, say, a 4 vector, so I should write it with the tilde because this is one form. This is nothing but u alpha df over dx alpha. But you recognize that this is the vector u applied on the function f. Okay. So we will write this, the basis omega a, as d of xa, because indeed when we apply d of xa on EB, this will be, because of this relation, this is just EB applied on xa, and this is d alpha beta, because this is d over dxb. Okay, so the basis for the one forms are the gradients of the coordinates. Okay. Now, out of forms and vectors, we can build up tensors. Should I go to that blackboard, or should I remain in this one? Is it okay, or? Okay, so for example, I can build up a tensor v by this cross product, and this is just defined as a linear operator, which when applied on two functions, let me call it h, because g in gravity is a bit kind of misleading. So this is just uf times v of h. So this is an operator which acts on two functions and returns a real number, and it's linear in each of the slots. We call this one slots. Slot 1 and slot 2, say. And of course, one can do, so this is nothing but ua df over dxa alpha, d beta over dh over dx beta, because this is how the vector is defined to apply on a function. Okay. Same thing we can do for one forms. One can, for example, introduce a tensor in this way, and this is defined as dxa dxb. Okay. Right. Then, as we know, alpha. We know that the gradient is defined on this way, and this d is this d is we will set that d applies twice on a differential will be 0 actually. So this one states that the df it's a pure differential actually. This operation on df will be 0. D of d is equal to 0 actually. This we will use it later on so that's property of this d operator. D operator can be applied to other forms, but for now I only apply to one forms. Okay, so a d over one form, it's a d of a gradient is 0. Okay. Okay, now we have, then we have the metric tensor. We will have the metric tensor G, which is applied on two vectors and returns a real number. So this must be a two form. Applied on U and W. And because this is linear in each slot, this is dx alpha over U dx beta over W. And it is U rho alpha E rho W sigma dx beta E sigma. But this is nothing but a delta function. So this is nothing but this. Okay. Right, so out of a metric tensor and vectors, we get scalars. Now, okay. Now, this is like GIAN. This is just differential geometry. Now, in cosmology, we impose symmetries, and in as a first approximation, we say the universe is isotropic and homogeneous, actually. Of course, we know this is not the truth. The universe is not homogeneous and isotropic, actually. So when we study cosmology, the background, I would say the background cosmology, we do impose that the metric describes a manifold which is homogeneous and isotropic. But we know that this must be just an approximation. The real metric would be different from the one we usually consider, actually. So when we study cosmological perturbation theory, we choose a different metric. And that different metric is supposed to give more precise information about the manifold we have. But to say, for the moment, where did I put?
Excuse me.
Yes.
How does it connect to general theory of relativity or Minkowskian metric? This metric, how is it related to that?
Yes. So okay. Yeah. So right. So once we have the metric, actually, the metric defines, say, the variable, the field we have, no? So in order, then Minkowski is a particular form of that metric. And by using that link you want will come from the equations of motion. So given some equations of motion for the metric will be sourced by some other fields, matter fields usually. And we will see, but in standard general relativity, Minkowski is a vacuum solution. which means if I have no matter field, one solution is Minkowski, actually. So but we have to assume some equations of motion, okay? So we have to assume some Lagrangian, if you want, some action, for example, the Einstein-Hilbert action, solve the differential equations given, given the matter fields which are present, actually. And one solution is, of course, is Minkowski solution, but it's not the only solution, actually.
And this is more general mathematically.
Yeah, this is more.
Relativity and
Right. So
basic fundamental.
exactly. So this comes from the definition of the field we are considering. So as for now, we have not introduced any action or any dynamics for this object here. This is purely formalism at the moment, actually. But one may say, okay, suppose I have a metric which is defined as, here I didn't say, but this object must be symmetric, actually, this GAB. And it has to have, Minkowskian signature, meaning that, this is a symmetric matrix. So at any point, it can be diagonalized through a coordinate transformation. At any point, it should be possible to write it down as a Minkowski at any point. But even though, so this is true whatever theory you have, actually. The point is that we should not expect that this Minkowski theory evaluated at one point to be true in any other point of space-time. Right. But given the answers, the universe is homogeneous and isotropic, actually. Leads to the following. Notice these are not anymore bigger.
A little bit bigger so that this is.
Okay. I got scared for a moment. I said, Mr. Einstein came here. I'm going to talk about ghosts, okay? But that's not the case, okay? Yes. Okay, I hope this is a bit bigger. Yes. Okay. Now, so now this is just, so if this is true for any little displacement, actually here, for a homogeneous and isotropic universe, we can write this one plus r squared. So this is written in all textbook, where this one is the ansatz given a manifold which is homogeneous and isotropic, even without knowing the Einstein equation, one can write this one. Of course, this is not complete because here we know. By the way, so this k is big K is just a constant, and here we have a function of time actually. So in the following, I will consider only for simplicity, actually, but nothing changes in terms of the physics, the case k equal to 0, which means that this one becomes just 1. And as you recognize, this part can be rewritten by, this is the standard metric of the three-dimensional space using here polar coordinates and here Euclidean coordinates. So I will focus on this one, actually. This, as I said, first of all, it fits very well the data, as far as we know. And second of all, for this kind of introduction that I'm going to give a cosmological perturbation theory, it's a simplification which is very useful, I would say. But there is nothing. We can also study different spaces, actually. But most of the times in cosmology, in research paper, we usually use this approximation because it's a very good fit to the data, actually. But the only point here, we have this function of time, and this is unknown. This is unknown, and this is what the equations of motion will tell us, actually.
Antonio, this metric is homogeneous and isotropic.
Yes, yeah.
But this is only for co-moving frame, fine? Because you choose a preferred time.
Yes, exactly. Yeah, this is a good point. I mean, of course, we are in general relativity. We can change coordinates as much as we want. In principle, one could choose coordinates for which this doesn't look at all like this, although it's the same manifold, actually. So yes, we can choose this kind of coordinates for which the metric looks like this, actually. Yes.
I have one more question.
Yes.
What kind of metric will you have for a only homogeneous universe and another metric for only isotropic universe?
Yeah. So, for example, so suppose that I choose the metric to be anisotropic. I could put here, say, a function of time. Because here I would say like x and y and z are different. Oh, this is called, by the way, Bianchi 1. Okay, if I call this one, this is a Bianchi 1 kind of universe here, where actually Bianchi 1 has no. Bianchi 1 would be this kind of thing, actually. Okay, something like this, actually. So one is different from the other two, actually. And you notice here it's still a function of pure time, actually. So at any time t, I have at any time, if I choose t in terms of t naught, so this becomes a constant, right? At one single point of time, actually. So I can rescale this one at one single point of time, x, such that this, or y and z, such that this constant is, so at one point it looks like homogeneous and isotropic. Okay? Non-homogeneous, then you have to introduce some x dependence.
Gauging it. Kind of gauging it.
Yeah, kind of gauging it, yes. But so the crucial point is that really, in our case, we will assume that at a very large scale, the universe has a very, very simple form. Because this is one of the most, okay, except Minkowski, this one is one of the simplest possibilities we have in general relativity. And I say general relativity, but this goes beyond general relativity, okay? This is for any theory, as long as we suppose there is a metric tensor. Okay. Now, as you can see, if I have a flat metric, indeed this coordinate looks slightly simpler than this one, actually. And in particular, we can write down, I can make even a time redefinition here. So many times in the papers, you will find this kind of form, okay? Where this is the 3D element, and there is this time, and I made a time transformation here such that I have a free function of time here. It's not really needed, okay? In general relativity, I can make another t transformation such that this becomes maybe a squared, and then we have a conformal time. I have 1, and then this becomes universal time, and so forth and so on. So, right, so when we say to students, look, the universe is described by this object here, actually, it's a bit a bold statement, right? Because this is a very, very simple thing out of a very complicated system, actually. But anyhow, so out of this metric tensor, we can find the Riemann tensor. I don't know. I don't want to go too much into the details actually. So this will be the starting point. This is background Friedman Lemaitre Robens worker. I should say flat. Flat because we chose the k equal to 0. Yes.
So in the definition of the metric tensor,
Yes.
the symmetry, the fact that the metric tensor is symmetric, does it follow from this definition?
No.
Assumption.
Assumption.
So, but also you can see that G alpha is a dx alpha dx beta.
Yeah.
Alpha dx beta is a symmetry. So that always symmetry.
So if G alpha beta has antisymmetric part, it would vanish. Okay? So this object here selects the symmetric part of it. But G alpha beta in principle could, in itself could be, but no, we'll take here the G alpha beta to be symmetric, okay? We impose. All right, so now what I want to do, okay, so this will be the starting point, and the next thing I have to do is to introduce the perturbation variables, actually. But before doing that, I want to deal with matter fields, actually. So how long do I have before?
Another 40 minutes.
40 minutes. Okay.
This is all in 3 plus 1 dimension.
Yes, correct. What I'm going to say, this cosmological perturbation theory, of course, can be extended to, who asked the question, actually? Who said the 3 plus 1 dimension, actually? Okay, sorry. Just because I wanted to know who I was talking to, actually. So, the same formalism can be applied to any dimensions, actually. Only point that when we study cosmological perturbations, we should first assume a background, and the background must have some, interesting phenomenology. Or after we are sure about a background, then one can study its stability, actually, or the properties of the gravity around this background. You see, when we study cosmological perturbation theory, yes, we want to study whether a solution is stable. But not only that. We want to know how the universe behaves, whether if it's not exactly homogeneous and isotropic. Okay, so let me introduce the concept of perfect fluid. Okay. So we will assume that whatever field we have, whatever fluid we have, the number of these fluid components is constant, okay? So we know that we assume that a perfect fluid satisfies the law of thermodynamics, the first law of thermodynamics, and then we will consider quasi-static processes for which we can introduce the heat as the temperature times the increment of the entropy. So let me rewrite this one into this form. Okay. Right. Next thing I want to do is to promote this differential in terms of one form. So we'll write, this is the one form is equal to P one form V plus one form E. So I promoted this differential, which were numbers, into operators, which act on vectors. Okay. Right. Then what we are going to do? Oh, but I say so when we say V and N, what I mean is that that's the volume measured by an observer which is at rest with the fluid. And that value will be invariant. Okay? So that's important. When we introduce rho, for example, the energy density, that is the energy density measured by an observer which is at rest with the fluid. It's the proper volume. When we say volume here, it's actually the proper volume. Okay, so then let's introduce the entropy per particle and the energy density, which we'll define here as E divided by V. And also let's introduce N to be the number density. Right. Then this relation becomes the following. Let me say, okay, so N0 T ds is equal to P. I will write V in terms of N. So this will be N0 divided by N. So this will be N0 times the differential of 1 divided by N plus differential of rho B. I should remember to write a bit larger. Okay. All right. Then this relation becomes N0 T ds equal to N0, let's say, minus 1 divided by N squared P dN plus, this will be N0 differential rho divided by N. Okay. So I can divide by N0. And I will have T ds is equal to minus P divided by N squared dN plus the rho divided by N minus rho N squared dN. Okay, so this one can be written as minus rho plus P divided by N squared dN plus d rho divided by N. Okay, so this relation, as it is, can be applied also in cosmology, because in cosmology we have energy density, number density. We don't know the exact volume, but we know the total volume, but we can still know what is energy densities. And another thing that I want to do, I want to introduce mu. So mu n we define as rho plus P. So then this relation becomes the following. D rho is equal to mu dn plus nt ds. Okay, so all right, so this is the first law of thermodynamics applied to perfect fluids. Okay, but when we write this equation here, this is really thermodynamics. Everything said so far. When we write this differential rho, this must be a real differential. So this means that mu and n is one of the variables, but mu and t must be functions of n and s. So what I write here, I write the following things. So a perfect fluid is a system with two thermodynamical degrees of freedom. In this case, one can choose any of the two. I can choose rho n, rho s, or any other, actually, but always two. No more and no less. Once I choose, say, for example, ns, then I had to give two equation of state. Equation of state. So a perfect fluid is defined out of two equations of state. If I don't give two equations of state, my perfect fluid is not uniquely determined. These two equations of state are not exactly independent, because I had to impose that d rho is a differential operator. Or if you want, cross partial derivatives must be the same, actually. So d rho over dn ds must be equal to d rho over ds dn. Okay, so I have this constraint here. Okay, so let me write. So we know d rho, because rho is a variable, and so rho, this implies that rho also will be functions of ns, because I have two thermodynamical degrees of freedom. Rho can then be written into this form. Okay? And then we clearly see that mu is d rho over dn at constant entropy, and nt is equal to d rho over ds at constant n. Okay? Right. Now mu was actually rho plus p divided by n, actually. So p is equal to n d rho over dn at a constant s minus rho. So the point is that once I give you these two equations of state, then I am able to solve for rho, and once I have rho, I also have p, and then I have everything. So then the system is uniquely determined, actually. And as I was saying, here, we have to impose. So this is the first derivative, and this is the second partial derivative. So we have to impose that d mu over ds at the constant n must be equal to d over dn of nt tn at constant entropy. Okay, so the cross derivative, d square rho dn ds must be equal to d rho square ds dn. So this is this formula here. So as I said, mu must be given in terms of mu and t must be given in terms of two equations of state, but these two equations of state must satisfy this constraint. Okay? Once that constraint is satisfied, I have perfectly determined and sensible perfect fluid object.
Can the temperature be taken to infinity in any situation here? Big Bang?
What happens is that when t goes to infinity, okay, so when t goes to infinity, usually the equations of motion will relate matter to metric, and this will tendentially lead to singularities of space-time. When we approach those points, then all these theories, which are effective theories, actually, will break down. So in the close to that point, we had to change the theory. If in the evolution of the universe I get points where t goes to infinity, that just means that at some point this treatment will break down, and we have no clear understanding what's going to happen. Yes.
In the beginning, you told me that the number density, which comes from the total number of particles or total volume, it has to be constant because we are measuring them as invariant quantities.
No. What I mean is an invariant. So what I mean is that the volume may change in time.
What did you mean when you said that volume has to be invariant?
So what I mean is that if the volume measured by any observer will agree, okay? At any time, it's like the proper time, right? The proper time, everybody will agree on the proper time that my watch is pointing. But my proper time is changing.
And a particular
Yes. Yes. Okay, so, right. Now, so once we gave these two equation state, which satisfy this constraint, then the first principle of thermodynamics, which is the rho, which is nd mu minus ntds, can be solved for rho. And once we have rho, we can solve for p, and then that's it, actually. Now, I will introduce for matter an object which we will see later on, which is the speed of propagation. Let me rewrite into this form. dp over the rho at a constant entropy. Inside the physics, this is the sound speed inside my material. And we will see that this comes also in linear perturbation theory when we describe a perfect fluid, actually. Now, what is this? Yes, so, all right, so that's, so what I want to write now is the following. So I want to write the same thing here. So we do a little bit of exercise in thermodynamics, actually. I'm not sure whether, well, I want to do it. Okay, so dp into dn plus dp ds. So here I have assumed that P, because I have a perfect fluid, can be written in terms of two thermodynamical degrees of freedom. Okay. But I can use my, and I think I made a mistake here. Sorry. It was mu dn. So I can rewrite my dn in terms of the first principle of thermodynamics, and I will get 1 divided by mu dp over dn, at constant entropy times d rho plus, and then I will have dp over ds at the constant n minus, because I have this term here, minus dp over dn at constant entropy nt divided by mu and times in ds. Okay, so what I wrote here, first saying that P is a thermodynamical quantity in terms of Ns. And here I changed the equation between rho and S. And the reason why I wanted to do this, because Cs squared is dP over d rho at constant S, actually. So I cannot write it to be this. This would be wrong, actually, but it will be this. Okay. Right, so right. So having now written this one, this will be just 1 divided by mu dp dn at constant entropy. Okay. Right, so P then is mu n minus rho. And what do I want to write here? Ah, yes, sorry. Okay, no, now I have this one. And remember that it was dp is equal to mu dn minus nt ds. So this means that dp over dn at constant s is, sorry, what am I writing here? Mu dp dn. We don't want dp d rho. This was the rho, right? Right? This was the rho, actually. Right, so, okay, maybe, okay, so let's do it. Okay, so dp dn will be, at constant entropy, will be d mu dn at constant entropy times n plus mu minus d rho over d mu at constant entropy. But d rho over d mu at constant entropy is mu. Okay? So this is n d mu dn at constant entropy plus mu minus mu. So this is n d mu dn at constant entropy. So this one can be written as n divided by mu d mu dn at constant entropy. Okay. Right. So now mu was d rho over the n at constant entropy. Right? Mu was d rho over the n at constant entropy. So this one can also be written as n divided by d rho over the n at constant entropy. And then here you have the second derivative of rho with respect to the n square at constant entropy. Okay? Okay. All right. So, okay. So this is for now a definition and the consequences of the first principle of thermodynamics, actually. Okay. Let me go there. So let's consider now barotropic fluid. So barotropic fluid, by barotropic fluid, I will, no, we mean, we give an equational state. Okay, so essentially we say that dp over ds at constant rho equal to 0. So what I mean here is that because indeed, if I integrate this one, I will get this equation here. So in this case now, the pressure has become only functions of rho, and this is one, say, a given function of rho, and this is one equational state. Still, I need another equational state to fully determine the perfect fluid. Okay. Right. We will use mostly barotropic fluids, actually, but not all perfect fluids are barotropic fluids. Okay, so did I write down here? I think. So we already wrote here this thing here. So now we have dp over ds at constant rho to be 0. So now we had to consider now this part of the equation here. Okay. Okay. Right. And remember that Q is equal to mu n minus rho, which is equal to n d rho over dn at constant entropy minus rho. Okay. Then we had to impose that dp over ds at constant rho is equal to 0, which, if I get it from here, this is equal to dp over ds at constant n minus dp over dn at constant s nt divided by mu. And this must be 0. Okay. So this implies that dp over ds at constant n must be equal to dp over dn constant entropy times nt divided by mu.
And then can we explain why for a barotropic fluid del P by del S at constant rho equal to 0?
This one, huh?
Yeah.
Once you integrate this one, you get this. Because this means that if this is a P is a function of rho and S, right? So if I take a derivative with respect to S, that will be 0. It means P is just a function of rho. No, this is, eh? No, rho, no, this is partial derivative. When we take the derivative with respect to S, keeping during the derivative rho to be constant.
So you are assuming, okay, so your two variables are initially n and s.
Yes, so P is So I have a system with 2 degrees, 2 degrees of.
Okay, so you are replacing n by rho. So you are assuming your number density is actually related to the energy. Because to start with, you said that everything you have 2 variables, which is n and s.
Yes. So I can choose any 2 of them, in particular rho and s, p, rho, anything. So in particular, if I consider p to be a function of rho and s, then dp, yes, so this thing is so now what I want to say, what I want to see exactly is what happens to this relation when p is a function of ns, say. That's exactly what I want to look to find actually. And I get this thing actually. So a perfect fluid which satisfies this relation is actually a barotropic fluid. Assuming that I have all my variables to function of ns, because this is the partial derivative with respect to s a constant n, and this is ns. T is supposed to be known because T is an equation of state, actually. T must be given as an equation of state of ns, actually.
So, but here you are putting condition on P, you know that P is only a function of rho. Due to that only you can get dp by gamma b by gamma ds equal to 0.
Yes.
Okay.
Yeah, and then I said that this one
Yeah,
implies this one.
yeah, that is okay.
Okay.
Pressure actually depends upon the entropy as well as the number density, but it becomes a barometric fluid only if the two balance out.
No.
The variation is still there. The variation is still there with respect to entropy as well as with the number density of the particles. But when the two variations, as suggested by the equation, they balance out each other, our fluid becomes barometric because the dependence goes only to rho.
Yeah, you can say, yes. So the point is barotropic fluid is.
It is variation exists everywhere. Mathematics says that
Yeah.
variation is everywhere. It is varying with respect to rho, it is varying with respect to s, and it is varying with respect to n as well.
Right.
Two
So
variations are actually balancing.
yes. In particular, I cannot put n here. This must be clear, okay? So this is a particular variation of rho with respect to some variables. Okay, so, all right. Yes. Okay, so okay. All right.
Now, what happens when you take only adiabatic fluid when the entropy is constant? When entropy is constant?
Yeah, so, okay, so this means that, okay, so you give some equation of state, okay? For example, P is a function of ns. Now, you take variation, and then after, so this is just a function in terms of ns, okay? It doesn't tell you that s is constant, n is constant. This is just a function of two variables. So you don't need to impose, dynamics on it. This is just as a law, P must depend on n and s without knowing anything about their dynamics. So this means that after you know dynamics, then, for example, okay, that's a very good point, actually. That's a very good point. All right, so So for example, when I have d rho is equal to mu dn minus nt ds, okay? Now suppose, now in principle, this would be, no, this would be, I evaluated them as one forms. So in particular, if I evaluate this one form over the time vector, so this will give you to rho dot is equal to mu n dot minus t nt s dot. Now this quantity in cosmology will be 0 because the entropy of the peripheral fluid doesn't change. Okay, then it means that on the cosmological background, rho dot will be mu n dot. But remember that also n was n0 divided by volume, right? And volume in our finite elementary Wolke will be a cubed, proportional to a cube. So this means automatically that we have so rho dot is equal to mu n0 divided by a cube dot, mu n dot. So this will give you mu n0 minus 3 divided by a to the fourth a dot. Okay? But mu is rho plus p divided by n. And n0 divided by a cubed is n. And get here minus 3h, where h is a dot divided by a. So this n simplifies, and we get that rho dot plus 3h, rho plus p equal to 0. Okay, so and this is the standard continuity equation in cosmology, where I assumed here, but after these thermodynamical things, that I impose dynamics. In particular, s dot equal to 0.
I was curious to know that what happens to that relation if you put it for an adiabatic. You assume barotropic fluid and also adiabatic. Then what happens there?
So by adiabaticity, you mean that
Is it constant? Then you don't write del T, del rho, del T, del S at constant rho equal to 0. That is then can I get an relation like that?
aha, so you don't impose barotropic, you mean?
No, barotropic is there, but for adiabatic condition, I cannot have that equation, right? Because your S is constant. So then what that relation will be corresponding to that?
Then rho is a function of n only, right?
Yeah.
That's the one.
Yes.
That's the one.
Yeah, function there. Yes, true. True. Okay. So okay, so let me give you. Oops, I erased the important point here. So let me give you one simple example. So let me remind you that, okay, so we wrote down CS square as n divided by d rho over the n at constant s, and then d rho square dn square at constant entropy. Now, we will define dust to be the object which satisfies two equations of state. Over.
You just stop after writing this dust, right?
Okay.
Stop after 2-3 minutes. There is some prayers today, special day.
Okay.
So write this.
Okay. So we will define dust fluid as, I had to give two equations state. The first one, t equal to 0, and this will be m0n, where m0 is just constant, okay, purely constant. Then, as you can see from this relation here, Cs square will be 0. Okay? So once we give the equation of state, we know the fluid, and we know also the speed of propagation. So for fluid, for dust, this is, because there is no interaction among the particles, so there is no propagation of information, actually. I think then maybe we can stop here. Yeah. So I think we had d rho is equal to mu dn. Sorry, mu dn plus NPDS. Or when we wrote with P, I forgot how, but anyhow, so any of the two is the same. So then you ask me what's the meaning of this constraints, right? On the so you mean d mu over the s at constant n equal to d n t over the n at constant s. Right.
What does actually mean physically for a perfect fluid like this partial derivative should commute? We can exchange the position partial derivative. First you can take the partial derivative with respect to n, then ns, or with an s, then an n, and simply the result remain to be invariant.
Yeah, otherwise you cannot find a function rho which satisfies this relation. I mean, this relation is also called integrability condition. Because once this thing is realized, then you can integrate rho.
So it is an exact differentiation.
Yeah, so rho can be exactly. Right, so remember that we had the Cs square was dp over the rho at constant s. So for a barotropic fluid, you see clearly that since p is just a function of rho, this becomes really like a standard derivative, actually. All right, what do I want to say? Yeah, okay, so right, so remember we got this relation here, actually. Okay. Now, you see that, so nt is equal to d rho over ds at constant n. Okay, so and mu is d rho over dn at constant s. Okay. All right. So then, mp is given by this relation. N d rho dn minus rho. So I can put this equation here for p plus those two constraints for mu and t into this equation here, getting just partial differential equation on rho as a function of n and s. Okay, can you see? I mean, this is d rho, and also the pressure can be written d rho over dn. And that equation actually leads to the following relation. Okay, so that relation goes into, I call this quantity A to be n d rho over the S at constant n, d rho over the n squared constant S, minus n d rho over the n constant S, second derivative rho dn ds, ns, plus d rho over dn at constant S, d rho over ds at constant n equal to 0. So that relation there implies this A, capital A, this quantity to be 0. Okay, so we get this partial differential equation for rho. Right, so now this A it can also be written as minus n d rho over dn squared constant entropy times d over dn of d rho over ds at constant n over n d rho over dn at constant s. So A equal, so this quantity here can be rewritten in terms of this one, and this must be equal to 0. Okay? For a barotropic equation state. Then you see, so the solution, so one solution would be n equal to 0, but we will not accept this one because that means that I have no particles. And another point will be this d rho n over the n at constant entropy to be 0. What happens is that that would be mu. Okay, this is what I call mu. No, mu is this one, but mu is rho plus p divided by n. So if I set this one to be identically equal to 0, I get the cosmological constant here. So p is equal to minus rho. Okay? All right, so apart from these two cases, which I will discard actually, then one we get this solution here that a barotropic equation state, a barotropic fluid for 2 degrees, for two thermodynamical degrees of freedom can also be written into this form. So in other words, this thing to be 0. Okay? But that one can be integrated, n d rho over dn at constant entropy. And this must be a general function of S. Okay? So, right. Now, this equation can still be integrated. You see, this is a function of S. You divide it by this. You multiply over there. And then you get that actually one can find that the solution, the general solution is rho is a general function of n e to the integral of S prime, sorry, S of S prime ds prime. So any general function of this form corresponds to a barotropic fluid. Okay? So notice that here I still have, it looks like I have 2 free functions, right? But remember that I have only chosen one of the 2 equation states. As I said, a barotropic fluid needs 2 equation states. So that's why still this one is not uniquely determined, actually. Okay. Now, but for a barotropic equation state, now we know rho. So, for example, we can write now what is P. Okay, here, because now we have rho. Once we have the solution, now we know what is the pressure. And let's see. Okay. Now what I want to study is the following. There is this part here. So let me study like a special barotropic equation of state P is equal to W rho. So once more here, this function could be a general nonlinear function of rho. Doesn't need to be linear to be barotropic. Now we assume this one to be the case actually, where W is a constant actually. Once more, this is one equation of state. So this will not fully define the fluid. Right, and then mu, which is rho plus P divided by N, will be 1 plus W rho divided by N. Okay? And T, okay, so T, but of course, yes, mu can also be found through this equation here, okay? Because now we have rho. So this was the definition of mu, if you remember. And yes. Okay, so now if I consider, so what is right. So okay. So now also I consider this. Okay. So let's see. So that one becomes. So I have that P is equal to N d rho over d N, a constant entropy minus rho. Okay. So that becomes N, which multiplies the derivative of this function here with respect to N. So I will get f prime times e to the exponential of s prime ds prime time minus f. And this must be equal to W rho, which is WF. Okay. So now it's so the solution for this one is when f is just a constant times n e for this integral ss prime ds prime to the power 1 plus w. Okay. So this equation here is solved by this, where this is a general constant and this is 1 plus w. Right? Okay. Also, notice that Cs square is dp over d rho at a constant entropy, and this will become just w. Okay? Right. So we already discussed the case for which the dust case just before the end of the lecture. So remember that, so this is rho equal to. So remember that for dust we had a T equal to 0 and pressure equal to 0. And so this corresponds to the fact that so rho was proportional to n because T was equal to 0, so rho can be integrated in this form. Mu dn, where mu is equal to constant. And s, this function of s, is equal to 0. So that this one vanishes and one gets only function of n, actually. So this was the dust case.
Why
No, this is an equation state. As I said, this is one equation state, okay? So we have to choose another one. And t equal to 0 is a possibility, which defines dust. So, what I call here dust is a thermodynamical system with t equal to 0. And p is equal to 0. Thank you very much.
By equation of state, we are having t equal to minus rho.
That one. It is one equation state. I need another one.
Okay. But here, if we conclude here, CS square comes out to be minus 1. Then the speed of sound is imaginary.
No, p is 0. P is 0.
Is the last line W after W rho? Last thing you have written. And after E integral minus F equal to W rho because we have divided T equal to W rho.
Sorry. No. Okay. So this differential equation is.
F equal to W rho. Because W comes from our equation at the top.
Yes. Those p is equal to W rho.
W rho.
Yes. Rho. Remember, rho was this general function of f. Okay. So this was this one. So yes. So for dust, I should say here, CS square is equal to 0. Now, if CS square is negative, then it's a problem, okay? And we will see this happens to some theories sometimes. And this one will be one of the things that people use to put constraints on theories, actually. Now, in this case, for dust, this is an equation of state, you see? Now, I think somebody asked me before a nice question. Yeah, I think you asked me what happens if for dark energy. Now, for dark energy, okay, so this is cosmological constant. Okay, cosmological constant satisfies this equation here. Okay, which is into this form actually, and W is -1. So then, indeed, for a cosmological constant kind of fluid, W would be negative and C squared would be negative. It doesn't need to be -1. In this case, it's -1, but anything negative would lead to this imaginary speed of propagation, actually. That is bad, okay? But a cosmological constant is not a fluid. Okay, in this sense, a cosmological. So if I put really p is equal to -rho, that's we will not call that one because that one we will not call that one when we say dark energy models. Dark energy models cannot be modeled by perfect fluids because anytime W tends to be negative, they will lead to instabilities. So perfect fluids are powerful to describe matter we already know. Okay. All right. So right. So there was another example that I wanted to discuss actually. So yes, I want to do that example. And let me use this. I'm going to use this part of, I'm sorry about it. Okay, so what I want to do now is to discuss the case of photons. Now, photons will have this equation of state, so we are in this realm here where W is constant is equal to 1/3. But let's not forget that photons also have some non-trivial thermodynamics. And we know that a gas of radiation will satisfy a Stefan law, right? So with proportionality sigma b, no? This kind of thing. So usually we don't see much this one in thermodynamics, right? I mean, this part of the dynamics of photon gas. We usually see that the other part, actually. But in cosmological perturbation theory, we would expect the temperature to have fluctuations, right? Instead, that's to have only like a fluctuation in the number density. But here, we would expect this field to have something more than that, right? Because we have some non-trivial temperature here. All right, so because W is 1/3, and so we know the solution in this case. So rho is equal to a constant times n to the this exponential in S of general function of S prime ds prime to the 4/3, 1 plus W. And then we know that the CS squared is equal to 1/3 from this relation here. So the speed is positive, so then it's a necessary condition for stability for the perfect fluid. Okay. Now, using the fact that NT was d rho over ds at a constant n, and put it into using this relation here, we find that this is actually no. Taking rho and from this formula here, T is equal to C1 to the 1/4 divided by 4 sigma b n e to the integral in S sorry, yes, S in ds prime to the 1/3. Because this was 4/3, okay. And, okay, I get this one. And T is 1 divided by n d rho over ds at constant n, which is 4/3 C1, and then I find an expression. Okay, let me write it down. So n e to the integral in S prime ds prime to the 1/3 e to the integral in S prime ds prime S. Right. So if I put this one to be equal to that, I get a solution for this function of S. So S of little s must be equal to 1 divided by S. So this equation state is equivalent to this one. So because of this becomes 1 by S prime, so this becomes the log, e to the log becomes S. So we get that rho is equal to a constant times ns to the 4/3. And actually, this constant can be related to sigma b. But what I care here, it's a constant. Now, what happens here? That so this is true for a gas of radiation gas. Now, in cosmology, S will be constant. So the only time derivative here will be n, which goes like a to the -3. Okay? So the fact that now I have the t rho is equal to 2 to the 4th, this will tell me that t goes like inverse a. Okay, so this goes n to the a to the -3, you get 4. It's 1 minus 4. Okay, so then in radiation, let me write it here. For radiation, T is proportional to 1 divided by A. Okay, so this is at the level of the background, okay? But there is something that we will see that radiation is a perfect fluid which is barotropic equations with barotropic equation state, but has some non-trivial thermodynamics in terms of temperature. Okay. All right. Okay, now what I want to do next yes, so what I will do next, it's the same fluid, but now we set the Lagrangian. Okay, yes?
So this does it obey ideal gas equation?
No. No, because for ideal gas, we have P is equal to NT.
So T is 0, P is 0. So this could
T equal to 0, if,
because then P equals to 0 implies T equals to 0.
right, but for ideal gas, temperature is not equal to 0 in general. So the ideal gas goes to a dust gas in the limit T goes. Actually, by doing the same thing, maybe I will have, I don't know, T will go like 1 divided by A squared in general. So it goes, it decreases faster than radiation, actually.
So this T equal to 0 and T equal to 0 are independent.
Yes, yes. So an ideal gas is defined as P is equal to NT, and then we need another equation state. Maybe you can put rho to be M0n. This would be the dust part, plus 3/2 n kT. Usually we put Boltzmann constant to be 1. Okay? So this would be the two equation state defining ideal gas, which are different. Okay? But it is true that in the limit T goes to 0, you get a dust.
What does the speed of propagation signify? We have introduced a term CS.
Right. So for now we don't see it. Okay. For now it's just we will see that when we do perturbation theory, we will see the meaning of it. Okay. So this one you have to keep it for now given. Okay. There is speed of propagation.
Something like that we have a speed of propagation and we get W, which is actually our dimensionless constant. And we are equating the two. We are defining CS equal to W, but we know that when we introduce the relation that P equal to W into rho, W has to be dimensionless because P and rho have same dimensions. And then we get CS square equal to W.
Yeah, but okay. So at this level, CS squared is just a number. Okay. I didn't tell you now it has also a thermodynamical meaning, but later on in cosmological perturbation theory, we will see why we call it the speed of propagation. Okay? Yeah, what I want to say? Yes, so this is ideal gas, dust. Okay. Oh, yeah.
Here you are taking condition for dust as T equal to 0 and P equal to 0.
Yes.
This is your definition of
Yes.
dust.
Yes, the fluid dust. Yes.
Fluid dust.
Yes. I should say that these two equations actually don't define a barotropic fluid. Okay? So P is not only a function of rho. As you can see, because you have T also here and N and T here, you cannot write P just as a function of rho. So this is the non-trivial example which goes out of the barotropic equation of state. These also will have consequences at the level of the perturbation theory for ideal gas. But ideal gas are not anymore studied much because we know that the cold dark matter fluid fits the data quite well, to be honest. Oh, another bad point about, this thing here, if this fluid really has a temperature, then you would expect in the past the temperature to be very high. But this is purely non-relativistic description, actually. In ideal gas, it's really not relativistic, actually. So even we have this one, we would think that at some temperature, we should change the equation of state of this fluid, actually. Anyhow, so. Okay, so what I want to do next is to introduce an action, okay, for the perfect fluid. And maybe I am sticking much to the perfect fluid, but I think it's a good example also, okay? Now, let me introduce this action for perfect fluid. The action for perfect fluid has a long history, actually. I think the first person who put some non-trivial action for dust was Weil, actually. Because we were saying, okay, I have T mu nu in general relativity, but what's the action of it? What is the Lagrangian? And people then, Weil was, I think, the first one who introduced perfect fluid for dust. Then other people, and to my knowledge, probably the first the first full description was Schutz in 1974. And the action that I'm going to write down was given by Schutz and Sorkin in, I think, 1 year later or something like that. So the action looks like this. I'm going to tell you that it looks weird, OK? And I think about it. It's a very interesting point, actually. And I'll tell you in a moment why. And notice that similar tricks have been used also in other contexts. But anyhow, so let me tell you what is this. So of course here is the Lagrangian perfect fluid, and then I put d for x with the minus d for x square root of minus g rho of n and s plus j mu d mu L plus theta d mu S plus sum over I between 1 and 2. It looks weird. You have to forgive me about this. Bi close. Right. So this is the Lagrangian which was introduced to describe perfect fluid. Now, why is it? It looks like okay. So there are many objects here. Okay. So first of all, rho is chosen to be function of ns. That's why also I chose from the beginning this thermodynamical thing to write down rho in terms of ns. Okay. Now S is a scalar, okay, which is supposed to be this entropy per particle object. Okay. Then n is not an independent. N will be the same, the number density, okay? But at the level of the Lagrangian is actually a non-independent, is not independent, but it's actually a function of this g alpha beta divided by square root of g. Now, as you can see, the square root of g multiplies rho, but the square root of g does not multiply j mu. So j mu is not a vector, but it's a vector density. Okay? And the vector density transforms exactly, if you do the calculation, this object here is actually a scalar. Okay? So notice that, so j alpha prime transforms as, say, epsilon times dx alpha prime over dx alpha j alpha. And this epsilon is the determinant of the inverse, dx over d x prime. So you will get twice the gamma, the upsilon, but you will get upsilon squared from here. They cancel, and then this one will become a scalar. I'm sorry, this one is, yes, okay. Right. Okay. Right. So anyhow, so here the variable, so n is not an independent variable, but the independent variables are j. I have this scalar here, another scalar here, I have another scalar here, and I have this I goes from 1 to 2, so I have a couple of scalars, 2 couples, okay? So I have lots of scalar fields, all right? So why did people introduce this action here? By the way, first question, is there a simpler action to describe perfect fluid? Yes, there is. Okay? So you are asking me, why do you take this complicated one? Because the simplest action we know about perfect fluid is not, strictly speaking, a perfect fluid. Let me tell you what I mean by this. A perfect fluid will lead us to T mu nu. Okay? And T mu nu is a tensor. So it's supposed to have some perfect fluid don't lead to gravitational waves, but lead to vector modes, okay, and scalar modes. We will see later on, okay? No gravitational waves, but scalar and vector. So if I use only one scalar, it's impossible to get vector modes from one scalar. Point here is that we don't use one scalar, we use many scalars. Okay, so mathematically question, this was addressed by Schutz. What is the minimum amount of scalars I need to describe a 4-vector? You know, so in some sense, this is part of the description of the perfect fluid, but we know that the perfect fluid requires u mu. Okay, because u mu is inside this definition here, right? So and the u mu will have so this is a 4-vector, but with the condition u mu is equal to -1. So we have at least three quantities that we have to adjust, right? This is 4-vector with one constraint. Now, indeed, it's possible to see that a general 4-vector can be written in terms of 4 scalars. Okay. Now here we have more than 4 scalars. Why Schutz and Sorkin? Did I say? Okay. No, this version is Schutz and Sorkin. So Schutz and Sorkin wrote down this one because using more scalars, they had the freedom to choose some fields which had some physical meaning. So even if the number of scalar fields are less, say 4, then those 4 fields may not have an easy physical interpretation. But here we have S, which we know what S is. And then we will know what is this L, theta. These 2 couple of fields will describe the vector modes present in the perfect fluid. Okay? So this action here is capable of, by the way, radiation fluid has vector modes. Okay? So then we had to be able to match them. And so this was, I think the action written into this way.
But in the expanding universe, vector modes they decay out, right?
True.
We don't need it. Why we need it?
You are right. But what you say is correct. I mean, the point is that they decay, right? They decay. It's true. But this is true for a theory which doesn't have any extra vector degrees of freedom. For example, suppose you take like this. You may have heard Proca theories or like this, no? And where you introduce an extra vector degrees of freedom, actually. Then you would expect those vector degrees of freedom to interact with your matter degrees of freedom.
But scalar field, right? So they also don't produce vector ones.
No, no, no. Eh?
Scalar field inflation also does not produce.
No. Okay, because you are considering a theory with scalars. What I'm saying, you know, a Proctor field is a mu actually. It's not electromagnetism because this one may be massive actually. Okay, so in some cases, I'm not saying that it's you know, in some cases maybe you may need to check what happens to the vector modes. Okay.
And gravitational waves can be formed in absence of fluid. I mean, even in perfect vacuum also gravitational waves can be formed. So
What do you mean?
we just need the gravitational waves are the vacuum solutions of Einstein's equation. So we don't need a fluid.
Well, hold on. I don't. Okay. We don't need the fluid to describe gravitational waves. You mean?
Matterless universe, we can have gravitational waves.
Yes, you can have gravitational waves, but you may have. I mean, okay. So maybe we can discuss later. Okay. So about. Okay, so now let's consider, let me continue with this one actually. Oh, notice, yes.
What will be wrong if you just keep the first term?
This one?
Understand, this is matter.
Right.
Density, correct.
Yes, okay, now let me give you the answer, okay? So suppose I don't want vector modes, I can neglect this part of the action. Suppose I don't care about the temperature, then I also neglect this part of the action. Now, suppose I only consider number, I can never forget about this. Okay, because n is a function of this j, actually. So what happens to this thing, this will set a constant number density. So constant number times a cubed. N times a cubed, yes. Okay, now. Okay, so what do I want to say? Yeah, I'll go like this. Okay. So once more, and actually we will do actually later on. If you know, in the simplest, oh, by the way, so even for the background, S is constant. So for a background point of view, we know that the background is incompatible with vector modes existing because we have isotropy. So then this part will be 0 on the background, which means that B can be said to be constant, say, for example. This S will be constant, but this thing must be kept. Okay? And this one will be there, although S will be a constant here for the background. Okay? So special cases for this one, you know, depends what you want, you see. Then you can deal with this action in the way you want. If you don't care about vector modes, it's also fine. You will not need this part of the action. Actually. If you don't care also thermodynamics, you also don't need this part of the action. To be honest, for barotropic equation of state, this part of the action will remain because this is related to temperature. But it will not enter in the Einstein equation motion. I mean, we will see probably. I don't know. But for some non-trivial part, it will be interesting to see what happens to T. Anyhow. Okay, so now let me take variation of S with respect to J alpha, well, J alpha up. When you do this, you will find that, so we take the variation with respect to J enters here in algebraic way, and J enters here in algebraic way, okay? So J doesn't have a derivative. So J mu sets constraints. There is no kinetic term for d mu itself. So J mu is a Lagrange vector multiplier. Actually, it's a vector with, it's not really a vector with density, vector density. Okay, so anyhow, so G mu, J alpha, on doing the equation of motion, you will get this is u alpha, where u alpha, I just call u alpha to be this quantity here. J alpha beta d beta L plus theta d beta S plus sum over I AI d beta BI. Okay? Now, I call this, so of course, when I vary this part, I will have this part here, which is enters here, and then I will have this. Now, if you see, so if you take this relation here and you calculate u alpha, u alpha, u alpha, u alpha is, you take this one, you will get minus g alpha beta divided by g. But this is, divided by g times 1 divided by n squared. But remember the definition of n, so this becomes minus 1. Okay? So u alpha is automatically normalized, actually, to what we want. So u alpha will be really the fall velocity of the fluid, actually. Now, to say that this object here describes a perfect fluid, we need two other ingredients. Okay, one ingredient is that the S over dg mu nu should lead to T mu nu, the T mu nu of perfect fluid we want. Not only that, but the equation of motion for all the fields must imply that T mu nu, semicolon nu, must be 0. Okay, those are the two ingredients we had to check. Okay, that T mu nu is the T mu nu of a perfect fluid in the way we know. And the second condition is that the equation of motion for the fields we have automatically lead to conservation of T mu nu. Okay, those two are necessary. If one of the two is not correct, then this is it's not a good action for perfect fluid, actually. What's that?
The dynamical part, the kinetic part of this scalar field. You write the interaction term only. You wrote the interaction only. J mu.
This is the action. This is the action. It's not that any action needs a kinetic term for your field.
I should get the equation of motion there.
Yeah. So what, for example, like the first equation of motion here for L will be d mu j mu equal to 0. For example, okay? Now, if in j mu cosmologically will be, j0, j alpha, and 0 on the background. Say, suppose I only consider background. J cannot have, sorry, this is function of time, okay? So J cannot have a vector on the background, okay, by symmetry. So this means that dt of jt will be 0. So j0 must be a constant. Okay, so this is, for example, on the background, and you see, if it is constant, you see what we'll get here. This will be a6, and then it goes like a cubed. Right? Because on the background, this is g00, which is minus 1. And this will be minus a to the 6. So we will get that n is proportional to a cubed on the background. Okay? So in other words, these set constraints.
These are giving only constant equations.
Yeah.
The equations of motion.
Yeah, right.
You write only the interaction part. the dynamical part do not present, then maybe
Yeah, this will have a non-trivial dynamics. Still, this one will have non-trivial. Okay, if you want, this is a good point in a sense. So what does this theory describe? Okay? So you asking me more or less if I understand this quantity, this question. What is this theory? Do I get some dynamics or only get, you say, interaction, you say? Notice one thing, though. J mu is a Lagrange multiplier. In principle, you could integrate it out, and you will get d mu square. It's just because we don't know how to integrate it out. Okay? But in principle, J mu is a Lagrange multiplier.